The scientific revolution starts now.
This is the Science Joy Podcast.
Let us see in the dark.
Nobody went there right after the impact. It was in 1908 because there was a war going on. And so people were busy with other things. But this guy, Kulik, came and took pictures of it. And so there was an area of 2,000 square kilometers, not 2,000, 2,000 square kilometers where the trees were all knocked down because this one was it was a piece of comet, I'm pretty sure. And so what happens is comet pieces are not very strong. So unless they're really huge, like the size of the KT impactor, the Cretaceous Tertiary Boundary impactor, they don't make it to the ground. They break up in the air, so you get a big air burst.
Yeah, it's like, how many of those do we not know about? I mean, if it disappears in 100 years, it's like...
Oh, it's a lot. I mean, there was one in Brazil in the 1930s, too. And then my Russian colleagues think there was another one up near the Urals that was just heard by a few geologists that were out there doing field work. And then there's another...
Is there perhaps someone sawing in the room?
Pardon?
Is there someone doing any kind of sawing in the room?
Oh, my husband is. I'll close the door.
Yeah, we could also try the background cancellation.
Yeah, we should do that too. And we should also but I want to do a clap before.
Oh, but this stuff's interesting.
I'm going to close the door.
I'm going to keep this stuff.
Okay.
I just need to do a clap.
Maybe we can edit it in the beginning.
Mm-hmm.
Yeah, so I closed the front door, so hopefully, because she's just repairing something outside.
Yeah, of course. Do me one favor before we get too deep. Can you give me one clap right in front of the camera? Perfect. Okay. And that way we can align the audio later because there's a little bit of a lag between video and audio. But we're recording at this point, and so conversation is casual. I think that we should just keep going right where we are right now, unless you have any questions or comments or concerns.
No, just, tell me what you want me to explain and I'll do it.
Excellent.
Yeah, I mean, what you're describing, having visited Tunguska and seen how little remains in the way of immediate evidence and how that plays out across history is just unbelievably fascinating to me. Just the gaps, I mean, in general, the gaps in our understanding about the deep past seem massive, seem expansive, and it seems like what you have been working on, this idea of scant but compelling evidence for ancient tsunamis, fits into that landscape of trying to look for something that's not so easy to grab a hold of. And meanwhile, history has been written in the absence of this evidence, and so you're working against the full weight of history at the same time.
Mm.
Yeah, well, there's a lot of things, like I think it was Thomas Jefferson was reported to have said that he didn't believe that, you ever got meteorite falls on land and rocks from the sky, basically. And yet in the Chinese history, there were records where thousands of people had been killed by a meteorite fall. So it's just like, it's like Western science didn't believe that the things that had been recorded by the Chinese because no Western scientist had seen it. So there's this huge credibility gap of, well, I'll only believe it if somebody with scientific training records it, and or they have a photograph or they have data. And in fact, there's also a lot of oral histories which, sound like they were impact events, and yet, a lot of scientists just don't want to believe that ancient people were really so good at recording what happened in the world around them, but they were in fact very astute observers of the natural world. They had to be. It had survival value.
Yeah, this level of detail that we expect today from scientific publication is really modern invention, right? This isn't the standard at all for most of human history, and there's just these chunks of data that are recorded in ways that we're not familiar with from thousands and thousands of years ago, potentially. I mean, most cultures were organizing their knowledge bases through other modes, through religious ceremony, through myth, through poetry, through song, ways that we can hardly conceive of in terms of describing the natural world in any serious scientific sense today.
Yeah, and the other thing is that, like now, like where I live here, I can't see the stars. But ancient people, they could see the stars. They could see what was going on in the sky. And they used that astronomical knowledge to do things like tell them when to plant their crops. I mean, in Aboriginal cultures, where people lived on islands, they can use that to tell them about the weather, when's a good time to go fishing. There's a lot of things that if you're an astute observer of the natural world, they help you get food, live a better life, avoid disasters. I mean, like the 2006 Boxing Day tsunami in the Indian Ocean, cultures where they had an oral tradition that said, okay, if the sea goes out and it goes out way farther than the lowest low tide, just turn around and run inland or climb a palm tree. In those cultures, fewer people died or nobody died. Whereas in the cultures where this kind of ancient knowledge hadn't been preserved, then people were killed by the tsunami.
And you mentioned the sky too but not only it being practical, it was also their Netflix and everything, right? That's what they had at night to tell stories by. And so the stars served as a sort of map onto which they could place their mythology and have it transmitted visually to the next generation, I imagine. And so a lot of these stories played out. I think there's something humans need about the TV. That's what's funny about it, is we all complain we shouldn't spend so much time watching TV or whatever, but there's something deeply ingrained about us that needs this visual mythology. And I think that it's really, really ancient and it is practical, like you say, in terms of how these mythologies teach us how to live and what dangers to avoid and what pitfalls await us if we behave in, unscrupulous fashion, perhaps.
Yeah, but it's more than that. I mean, in these ancient cultures, people would tell these stories over and over, and the people who are chosen to keep the stories, I mean, there are people who can remember things word for word, verbatim. They just don't forget. They remember everything. And those were the people who were chosen to transmit the oral history. So the knowledge was saved over, literally hundreds of generations. And, the stories didn't change much.
I wonder if we couldn't sort of go back to the beginning a little bit and have you introduce yourself and offer a frame for the work that you do, because you bridge this gap between the mythology and the geology in a really beautiful way. And I want to be able to hear in your own words the way that you see yourself and your project and your aspirations.
Well, I guess I've been working with people who collected some of these oral histories, and it was pretty clear that a lot of this, it's not just flood myths. There are also stories about hot water coming from the ocean or from the sky. There's things about where just before they have, this huge flood, huge deluge of rain, they'll have like, hot objects coming from the sky. So they're in those particular, oral traditions, there are things that sound very much like they might be an impact. And so I got interested in that. And also there was work of other geoscientists, particularly in Australia, because Australia is in an area where, you're pretty far away from any active subduction zones where you would have which, in subduction zones you generate tsunamis. But Australia has these tsunami deposits on both sides of the continent where they go, kilometers inland and hundreds of meters above sea level. And the thing is, scientists have modeled, like a tsunami generated by an earthquake, like how far can it go above sea level and how far inland can it go? And some of these apparent run-ups they're too large.
How big are we talking?
Yeah, like 100 meters above sea level, 300 feet above sea level, and 5 kilometers inland. So they're and one of the Russian colleagues actually said that he doesn't think that an earthquake generated tsunami would go more than about 50 meters above sea level.
Before we get any farther, we have to take a very short break to ask for your support. Every single month, people support us for the work that we do because they think that what we bring to the world is valuable. And we couldn't do it without you. So if you like the podcast, if you like us encountering ideas, meeting new people, and exploring the very edges of scientific knowledge, show your support by coming over to Patreon. If you can't come over to Patreon, that's fine. Leave a comment. Tell your friends about the podcast. Come to our Discord, encounter the conversation there, and contribute to it. And that is also enough. But if you can, consider making a donation.
Or pick up a really awesome t-shirt, which is down in the bar below. It's obviously overpriced, but the donations are going towards building this program into a bigger and better ship. All right, let's get back to the discussion. So that's like burying Portland, essentially. In sand.
It's 5 kilometers inland.
Oh,
Portland's 30.
I thought she said.
Yeah, that's
No,
pretty far.
300 feet, 300 meters tall, and then 5 kilometers.
So it's the run-up is the height above sea level that it goes, and then the actual height of the wave is about a third that.
I see. Well, I mean, Portland probably would be inundated because it's at a river, and so I can imagine that you have some kind of surge that goes up the river, right?
Yeah, no, Portland would be inundated if there was a big tsunami, and there is supposed to be a magnitude 9 earthquake. There has been one in that area, and there's supposed to be another magnitude 9.
Well, this is what's so interesting is that because it's never happened within living history, and because the mythologies of the area are relegated solely to the tribes people, there is not really a lived awareness of the precarity of Seattle and Portland and the entire Pacific Northwest coast. People are just kind of like, I mean... Yeah,
well, actually, the geoscientists are worried about it.
Yeah.
And they've actually been able to figure out when the last really big event was, because it was also seen in Japan.
Mm-hmm. There was also a really interesting. I used to give tours up by Portland, and there's a mountain there that crumbled. It was called Dog Mountain or something, and somebody actually dated it using lichen chronology. And so what they did is they looked to see the exposed rock faces, how big the lichens were on those rock faces, and then compared them to the size of the lichens on the faces that hadn't crumbled during the earthquake, and arrived at a date that was then corroborated by the Japanese date, which I thought was really interesting.
Yeah, no, and they also can use. For something that they can also use tree rings to date things, because tree growth gets disturbed there during an earthquake.
So just to I want to make sure people understand who you are, and you're a scientist, right?
Right. I'm a research scientist. I'm at Lamont-Doherty Earth Observatory. It's part of Columbia, but it's also its own place.
How'd you get your start into science? Were you always going after the tsunami question, or were you more interested generally?
I mean, my PhD was in marine geophysics. I went to sea, and I got interested in the tsunami question just because I read these papers by Dieter Kelletod and Anja Scheffers, and where they talked about in Australia, the thing was they could see these tsunami deposits, and the other thing about it was that the direction that the deposit that they were actually kind of these V-shaped things, and if you take the back, this is so that it came from the direction that's the opposite of the direction that the V is pointing.
Mm-hmm.
And the thing is, there was two theories about these things. One is that they were wind-blown features, and the other was that they could be tsunami deposits. But there's two problems with a wind-blown origin. One is that the orientations of these features were not in the direction of the prevailing wind. So, and the other was that they occurred very often in places where there was no beach. So there was no sand source for them that was at sea level. There would stand offshore, but not right along the ocean. So it made it, and even with sea level changing, it was still a problem to source the sand for these things from the wind.
Were there rational explanations for how the wind could have pulled this off?
Yeah, I mean, the problem, of course, is that once you get these things on land, the wind reworks them. So yeah, people had ideas that maybe they were, that some people thought they were from the wind, and it's tricky because, they can be a mixture. But I thought that the data that they had was pretty compelling, that these things were not windblown, and I really wanted to go look at them. And I did meet up with Ted Bryant, who'd worked on these things in Eastern Australia, and we went to look at his field sites, and there were places where there were things that just looked like it couldn't possibly have been the wind.
The papers that you sent us, I mean, the shape of these dunes doesn't, I mean, in order for it to be wind that made them, they would have to be winds that would scour the entire Earth flat, it seems like, right? They're very geometric, they're very jagged, they're very distinct in their shape and their orientation.
The shape itself isn't really what's so important. What's important is that first of all, we looked at them, and typical sand dunes that are produced by just the wind blowing them, they're 100% quartz, and these things have marine microfossils in them. And marine microfossils, the thing about wind-blown sand is, first of all, the wind can't transport material that's as large as water can. So, and these marine microfossils in the sand dunes, they tend to be only pitted on one side. And I think they were pitted by sand grains that were being blown around. But I think the reason why they're only pitted on one side is because the wind can't move them. And so they just get and the other problem with moving marine microfossils for tens of kilometers is the reason why most, if you go to the Sahara Desert or someplace like that, the sand, it's all quartz. And the reason why is that calcium carbonate or aragonite, they're both calcium carbonate, the material that marine microfossils are made out of, it's got what we call cleavage. So if you hit it with a hammer, it breaks up into these little cubes, they're actually not quite cubic. I mean, some people will have seen Iceland spar, which is the calcite from Iceland, where you can see through it, but it kind of moves the image to the side. So calcium carbonate, if you're trying to move it by the wind, what happens is that if you hit it enough, it just breaks up into little tiny pieces. And so you really can't move it a long ways without turning it into powder. Whereas quartz sand, when you move it, because quartz doesn't have a cleavage, so what happens with quartz sand is that you just kind of knock off the edges. It'll start out kind of rough on the edges, and then over time it gets smoother and smoother. And so these quartz sands, where they've been moved really long distances, the grains are almost perfect spheres.
That's really interesting. Is the calcite's lattice responsible for both its optical properties and for splitting it into these fragments?
Yeah. I mean, there are just some minerals that have cleavage and some minerals that don't. And so the ones that get preserved, also like in beach sands, they're another mineral that doesn't have cleavage is zircon. And if you go to the beach, you'll see these kind of pink bits of sand, like on Long Island, that's actually it's another mineral that doesn't have cleavage. So it's not zircon, although there might be some zircons in there. It's it's garnet.
Mm.
So you get pink garnet.
Mm-hmm.
But zircon's very important because the oldest minerals on Earth are zircon, and one reason why we can find them and why they've gotten preserved is because they don't have cleavage.
So let's see if we can get kind of a 30,000-foot view of the story that your work has uncovered, because does it go back beyond the Younger Dryas impact event, or is that where the oldest impacts that you're talking about start?
Well, there might be older events, but the oldest event that people have documented from oral traditions, I mean, in North America, they're talking about a Younger Dryas impact. They're also talking about something that's Younger Dryas in Syria. And it turns out I got these ages from the chevrons in Madagascar, and I said, okay, I'm going to average the ages because I had 3 different ages and they were close but not the same. So I averaged them, and they come out with an error the same age as the age of the start of the Younger Dryas. So those chevrons could have been formed by an impact into the ocean at the time of the start of the Younger Dryas.
And that's a pretty radical finding, right? Because so the Younger Dryas impact theory has been popularized, let's say, by Graham Hancock, right? And there's lots of problems with the way that Graham Hancock presents his data. I have kicked him on the show many times. I'm sorry to the people who love Graham, but there does seem to be a pushback in the academic community against the idea of a Younger Dryas impact. Like, for example, there was I think that it was Tal el Hamoum. There's this site in the Middle East where there's that black mat that was dated to be associated with the Younger Dryas, and it was published in Nature. And then there was another group that came around and was like, no, this is an evidence of a Younger Dryas impact event. There was no such thing that caused the Younger Dryas. This is all just nonsense. And so it feels like in the literature there's a very strong push and pull between the two perspectives, where some people have evidence for there being this impact event. And one of the papers that you sent us was you had sampled in 18 different locations around the world the presence of these microspherules and various other impact associated signatures that weren't present before or after. And so it seems quite plausible that there is evidence for that. And yet there's still a contingent of people who are like, no, it never happened. So like, what's going on there?
Well, I think there's, first of all, the people who've done all this spheral work, I haven't worked with them, but I think they're good scientists. But I think a lot of what happens is in geology, it's very difficult to date things exactly. So you're always like dating above and below. And the other thing is that the people go out and they say, okay, well, if there was a Younger Dryas event, there must be evidence for this event everywhere on the planet. And we know that there's erosion and that sediments accumulate in topographic lows. So there's never going to be evidence of a Younger Dryas impact event if what you happen to sample was a topographic high.
Hold on, can you explain? What's a topographic high?
So, well, you see it's really easy to see in the ocean basins, for sure, because when marine sediment, it just kind of, rains down from above. And then you can look at the sediment it's not as dense as the bedrock. And so when you look at a seismic reflection profile of the seafloor. You'll see the seafloor, and then you'll see this kind of lighter colored layer, which is less dense, which is sediment. And you can see that the sediment layers are thicker in the hollows. And the same sort of thing happens on land, but it's a little harder to image. Like, well, for example, if you have a lake, you're going to have thicker sediment cover on the lake, and very often on mountains, there's just rock exposed. There's no sediment, there's no soil at all. And so when I'm saying sediment, you could use soil almost interchangeably with that.
And when you're saying that it's easy to sample a topographic high and have that complicate the story of an impact, can you relate those two together?
Yeah, I mean, so basically, no matter what geological event you have on the Earth, you're never going to have a sedimentary record of that event everywhere on the planet. And there's just places where you don't get deposition. So that's really what's going on. And I talked about the wind blowing stuff. I mean, you could also, even if you had a fairly big impact in the Younger Dryas, if you calculate how thick that layer is going to be, like 1,000 kilometers away, it might be like a centimeter, probably less, like, maybe a few millimeters. So, and if it happens to be made up of material that the wind can pick up, then it's just going to get blown away. Or it'll rain, and the rainfall will erode it away. So that there's never going to be a uniform layer of impact ejecta over the entire planet, even for a pretty big event.
But go ahead.
I was going to say, in terms of the topographic record of this as well, it seems like we were talking before we started recording about the Tunguska events, and some of these impacts don't necessarily leave craters. They explode in the air, right? And so that must be playing into the mix to some extent too.
Yeah, it is. And in the oceans especially, because you have to get an impactor that's got a diameter on the order of the water depth in order to actually get a crater. And so the stuff that we saw in Madagascar, I found a crater candidate, but we still don't have detailed maps. There's somebody else, Henry Dick, found some interesting stuff near the Southwest Indian Ridge, and I've seen the topographic maps, and they're not very convincing. And I think the problem is the water's really deep, and so it's not so clear that you're going to get a well-defined crater. However, I realized that it is testable in that area if you actually had something hit the bottom, because you could go out and dredge it. You could go out and when you dredge, you tow a bag along the bottom of the ocean, and you could actually, and that would be the best way they do it mostly for getting rocks. And so you could tow a dredge across some of these, they look almost like pockmarks. And if they really were produced by an impact, I think eventually you'd get some bits of impactor.
And so when we're talking about this impact, where is it in the world?
It's in the Southwest Indian Ridge. He found something in the Southwest Indian Ridge. It's a little far away, or it's not exactly in the right place to have produced the chevrons in Madagascar, but it's in the right location to have produced a tsunami that then could have gone up to Réunion. And what's interesting about the chevrons in Madagascar, when I wrote the paper, I said, well, they could have been from a sediment slide on Réunion. It's a volcanic island that's owned by the French. Or they could have been from an impact-generated tsunami. But in fact, one of the things about a large crater is it also it produces a tsunami and it produces a large earthquake. So you could have triggered sediment slides in Réunion. There actually are some sediment slides that are, I don't know how well dated they are. I didn't get a chance to look that up, but they're roughly the right age. So it could have, and the interesting thing about the chevrons is that we only really they only really look obvious when you look at the map of Madagascar in the area where it's close to Réunion.
Mm. So why is there a preference against there being a younger Dryas impact? Like, it seems to me pretty obvious that if you have a sudden event that causes, let me start that again. So the younger Dryas is this period of rapid cooling that lasts about, I think that it's 1,200 years or so.
Yeah,
That is,
like that.
and so you have this glacial period. It starts to get warm, and then as it starts to get warm, all of a sudden you have a very discrete event where the curve of global temperatures absolutely takes a nosedive and goes down for 1,200 years. And after this period ends, it starts to go back up again. And it feels to me that the arguments against there being an impact event are not offering an alternative explanation for what the hell happened there.
Yeah, well, it's true. And I have to say that I think something happened around that time, that there was some kind of an impact, but was it exactly at the Younger Dryas boundary? I don't know, because there's also some ice core work where they've been looking for impact ejecta. And some people say they found something, and some people say they didn't. But they also didn't find any evidence for a big volcanic eruption. So it is very puzzling, and there are problems. Do we really understand the climate system well enough to know what could have triggered this? So I think something happened and that the oral traditions are recording an event, but we don't have a precise date.
And the oral traditions in this case is this hot rain, things falling from the sky. Do they talk specifically about there being waves and?
Oh yeah, there's traditions of tsunamis. Yeah, for sure. And what's interesting is I went back, there was a recent really large volcanic eruption in the Pacific called Hunga Tonga. And the thing about this is that it put like 20 times as much water vapor into the atmosphere as any other prior volcanic eruption in the modern era. And the reason why is because it was underwater. Mm-hmm. And the other thing is that it put water vapor like 50 kilometers up. So way up into the upper atmosphere. And they're still like recording the climate effects of this. So, and the higher you put stuff up, the longer the effects will last. So if you had a big oceanic impact, there's no doubt that it would have put huge amounts of water vapor into the stratosphere and even above the stratosphere, which would then take a long time to come back down. And there would presumably be some impact ejecta as well. So the amount of time that the climate effects would last would be long. And I can't say exactly how long, but and then the other thing that's really interesting about the Hunga Tonga eruption is one of the things that I found in the oral traditions, which I just kind of thought, oh, it's a big storm, you have this flood storm. But one of the things they talk about in some of the oral traditions is lightning. And it turns out that the Hunga Tonga eruption produced, much more lightning than they've ever seen from any storm.
Yeah, so I mean, what happened to the environs of Hunga Tonga after it erupted, right? Because I know that there was this severance of the undersea cables, and there was a big question of the devastation that was caused it was in Samoa, right?
It was in Tonga, yeah. Tonga, Fiji. It was in the Republic of Tonga.
Right. Republic of Tonga. Okay, so what were the experiences of the people that were there? Do we have oral traditions, or do we have oral stories of the people who were actually there when the volcano erupted and what they experienced?
Well, I mean, they got the people off the islands, but there was a tsunami, and it went up I think within 100 kilometers, the stuff I was reading said it went up to 20 meters above sea level. So that's pretty high. And some of the low-lying islands, there were a few people killed, because if people wouldn't leave, then a 20-meter high tsunami, I mean, it's going to kill you.
Mm-hmm.
And I know that in general, and also people told me that I was at this conference and they said that the people on nearby islands, there was quite a lot of ash, for example, on people's roofs, on people's cars.
Mm.
In fact, I know somebody who was in Australia, and he said that he got some ash from Hunga Tonga on his car, and that it actually scratched the car up a little bit.
Mm.
Yeah, I think people really underestimate the water contribution of volcanic eruptions too. I think that the total water content is the majority of the eruptive emissions, actually. And it's hard for us to imagine what putting that much water into the atmosphere does, because we think of volcanism, we think of destruction and gases and all these things that immediately affect us. But the climate impact of a serious volcano, and in the past, it seems like volcanoes have been much more active than they are today.
Yeah, it's hard to say, but I mean, the Hunga Tonga eruption was noteworthy because it put so much more water vapor into the atmosphere than sulfate. And sulfate is what usually affects the climate from volcanic eruptions.
That one was crazy. You could actually, I watched the pictures of it from outer space, and you could see the pressure waves actually nucleating clouds out at a distance as it radiated away. It was really something else. I can't even imagine what an impact even larger than that would look like, or how it
Yeah,
would.
and the other thing is that there was a pressure wave, a tsunami that was global. I mean, you're not talking about a huge tsunami, but you actually saw something globally. So in that sense, if you have a big enough event, you can see effects that are global.
And you would expect also to see effects that are not just global in terms of, these run-up dunes and spherules, but you'd also expect to see something in the human population, right? So are there studies that have looked for genetic bottlenecks or evidence of, massive population decreases around the same time as the Younger Dryas, or is this something that hasn't really been done yet? Do you know?
Oh, I think some people have tried to relate the extinction of the megafauna, I believe, to the Younger Dryas, but documenting changes in human populations is pretty hard. So they haven't really done it, and I don't know if they can do it. I mean, the best that I know that they've been able to do is there's a book called The 14th Century: A Distant Mirror, and in that book they talk about the Black Death and how it affected the population in Europe, and the basic way that they see the effects of the Black Death is that there were villages and towns that lost so much population that everybody left or everybody died, and those places have never been resettled.
Mm.
We've come across this a couple of times because there's we spoke to some archaeologists that are working on uncovering the Mayan highlands in Guatemala. And they talked about how there appears to be a period where everyone left the cities. And then after everybody left the cities, the language disappeared, and then the cities basically just were covered over by jungle. And now, they're finding them through LiDAR, but there was a distinct end to the inhabitation, and nobody knows why. And it seems possible that there was an event that was perhaps cataclysmic in terms of climate or volcanism or something else that basically motivated people to leave the cities, because if times are hard, the last place that you want to be is in a highly populated area, because resources are depleted much more quickly as a function of population. And so there does seem to be scattered through even relatively recent history this story of massive population shifts where centers of civilization are abandoned in favor of populations dispersing into the countryside. and our stories for why that happened are so unsatisfying.
Yeah, well, I think there's been more than one climate downturn in the past. It's not just the Younger Dryas. There have been smaller ones, and certainly, this 536 AD event. There were things that happened to populations. So yeah, I mean, people do get up and leave if the climate changes in such a way that they can't grow enough food.
Yeah, I just wanted to be clear that there are more than one of these events. So we've been talking about the most distant that you're studying, which is this Younger Dryas, which is 12,000 BC, I think, something like that. And you mentioned a couple of other ones, one around 3,000-ish BC, is that right? And then
I've been interested in the 536 AD event because that's the worst weather in the last 2,000 years. And I did some ice core work, and we found bits of we found nickel. Nickel is a considered kind of diagnostic of cosmic dust, and we found nickel iron rich bits in the ice core, but we also found tin rich bits, which I think are also cosmic dust. And the tin rich bits have iodine and xenon with them, and basically if you put iodine in the solar wind and you bombard it, you get xenon. Xenon's a noble gas, so it's you have to make it pretty readily before it can get into something. I mean, it's not going to stick around, is what I'm saying.
Now, 500 BC, we would expect some discussion of this in the early classical antiquity, right? It seems like they were quite illiterate. There was a number of literate societies at that time, right?
Yeah, well, it's clear that if you go to Egyptian history, that there are these intermediate periods when the civilization just broke down. And so, yes, I mean, there were definitely other times when the climate went bad and people, basically civilizations and cities require that there's somebody in the hinterland who can produce enough extra food to feed the people in the cities. And if you don't have that, you're right, people leave the cities.
So it's almost as if these are the periods in which the records would be absent because there's problems to be dealt with and nobody's sitting around getting paid to be a scribe in those moments, essentially.
Yeah, exactly. Like this 536 AD event, nobody even suspected that it existed until the tree ring people found evidence that when a tree is growing and it experiences frost during the growing season, you get what's called a frost ring. And they found these frost rings in trees in 536. And they did find, I think there are 3 or 4 descriptions of what happened that they did find in the written record. But considering that from the data that they have, that it was the worst weather in the last 2,000 years, it's amazing that nobody really suspected there was anything going on until they found something in the tree rings.
Tell us the story of how that discovery came about, maybe.
Well, I think the guy, Mike Bailey, who he's a tree ring guy he lives in Ireland, and he figured out that there was something going on. And then other tree ring scientists, found frost rings. Like there's only 2 events in the last couple thousand years that produced frost rings in Mongolia, and 536 is one of them. And so then Mike started looking in the records, and he found that there were descriptions like that, and also I think Richard Southers, where the sun would. There was an 18-month period in 536 and 537 where in Mesopotamia and Italy, the sun came out for only 4 hours a day. And also, of course, the crops were destroyed.
And is this written about in the
it's written
Mesopotamian?
about. And so the idea is that there was so much, in this case, volcanic ash, probably, maybe a little bit of cosmic dust, but I think it's mostly volcanic, that that the atmosphere, basically you have to have a huge amount of, aerosol dust way high in the stratosphere, because in order for it to be up there for 18 months, you have to, it has to be high. Because things that are lower in the atmosphere, in the next layer down, the troposphere, they get rained out.
Mm.
So for stuff to stay up there that long, and then the sulfate aerosol and probably some volcanic ash and maybe some clay as well, because I think there was probably an underwater impact associated with this event. Because we also found marine microfossils in the ice core, and so. So there was a bunch of very fine particles up there obscuring the atmosphere.
So where was the ice core? Where was the ice core taken?
Greenland.
Greenland. Okay, so you have the I don't remember the name of the scientist that you said who was in Ireland.
Mike Bailey.
Mike Bailey. Okay, so Mike Bailey, does he see the frost rings in Ireland, or he sees them somewhere else?
They see them somewhere else.
Where do they?
In Ireland, you don't get frost rings. It's too. What he saw were just basically low growth and he wanted the event to be around 540 instead of 536. But then and there is something around then too. There were two volcanic events, but basically the frost rings are mostly preserved in. You get some in the Soviet Union, you get some in Mongolia, but the big place where you see them is in the United States. In the bristlecone pines in California, and I think, Colorado, there's also some bristlecone pines.
Okay, so that's pretty crazy that you have something that is causing slow growth in Ireland, frost rings in Mongolia, California, the Rockies. Where is the and then deposition of marine microfossils in Greenland, which suggests that there's some kind of Are you thinking that that's tsunami event in Greenland that's depositing it on the ice cores, or how did the marine microfossils
No, I mean,
get there?
I'm thinking that you had an impact into the ocean, because they're tropical marine microfossils. They can't have come from the ocean near Greenland. They're tropical to subtropical. So, and this Hunga Tonga eruption is great, because what we learned from it is that if you have a big volcanic eruption and it's submarine, it puts material really, really high into the atmosphere, and so that makes it easier for that material to make it to Greenland or Antarctica.
So for the 536 event, are you thinking that it is an impact somewhere in the Pacific?
Yes.
Do you know roughly where? I mean, Pacific's
No,
big.
I've been trying to find it.
Okay.
But I haven't found it yet. I mean, I've got, seeing tropical to subtropical marine microfossils basically tells you that it's between, so if it's in Greenland, it's probably between about 20 south and 30, 40 north, because tropical to subtropical doesn't mean the same thing. They're diatoms. Doesn't mean the same thing as you would think of tropical. You would think tropical like within 30 degrees of the equator.
And when we talked before, during our pre-show, you were talking about searching for these gravitational anomalies. Is that the same strategy that you're taking for finding this impact event as well?
Well, I did try using that, and it actually, the problem is that the data, originally the data showed some things which turned out to be artifacts, but there are gravitational anomalies that have now been identified. There's only two of them that have been identified that I think are pretty certain. And one of them is in the Arafura Sea, which is between Papua New Guinea and Australia. And that one is interesting because the oral traditions talk about hot water from the ocean. They talk about floods, and they talk about hot material coming from the sky before the flood. And they talk about, there's also some stories about tsunamis. So it's all there. and this one in the Arafu Sea, I would like to get out there with a ship, but it's a little tricky because the water depth is pretty shallow.
And the shallow water depth means that there's...
It's harder to bring in a research vessel.
I see. How much depth do you need for a research vessel?
I think I wrote it down. It was like 46 meters of water.
Oh, wow. That is
So
shallow.
it's pretty. I think we can get a ship in there, but we also need some collaborators in Papua New Guinea, because it's very close to Papua New Guinea. So we need people in other scientists who are from Papua New Guinea who would let us within their territorial waters. So it's a you got to get it funded, and then you got to get all the political. You got to get your ducks all in a row to bring a ship there.
Yeah, these ships are what, $20,000 a day or something outrageous.
Yeah, I mean that's probably an underestimate. That's
Ouch.
Yeah, no, these things are expensive. I mean, it's not something that you could afford to fund out of pocket unless you were somebody like Bill Gates. So basically, yeah, you need to get a research vessel in there, and
it's probably not easy convincing Bill Gates that this is something worth his money.
No, I mean, he's more into medical things and pandemics, which is great. I mean, he predicted that COVID-19 was going to happen, and that we were underprepared for it. So yeah, I mean, I think his emphasis is great. It's just there are other interesting things to do.
So what does your process look like? So right now you have this evidence for an event in 536. Is
Right.
most of your time focused on building that story up and collecting more evidence for that, or are you on the search for other impact events? Because it seems like if we have this thing in the Younger Dryas, then we have another one that was about 3000-ish BC. I think that you have it at like 2880, maybe?
Yeah.
Okay, and then so we have this other one at 536. Are you thinking that there are other ones that are distributed
I
throughout
think
history?
there are multiple events. So there's a number of ways you can go. I mean, what I'd really like to do is to get some bog cores from Australia, from high altitude bogs, because then because the two crater candidates that show up in satellite altimetry are both relatively close to Australia. One of them is in the Southwest Pacific. I mean, the closest landmass is New Zealand, but if these high altitude bogs are nice because if you find things like marine microfossils in them, particularly carbonate ones, if you're far enough from the ocean, it's clear that they didn't come from just the wind blowing them in or some bird bringing them in.
Mm-hmm.
So there'd be a number of ways. One is to try and get a ship out there, but another is to look at stuff on land and try to reconstruct the history that way, because then you could see multiple events.
And what does your process look like? Because it seems the world is so big. That sounds so naive to say that, but sometimes I'm just struck by the difficulty of being able to look at a landscape and piece together what happened to it under so many layers of events, right? Because we live in the Pacific Northwest. We go out into the woods, and it's obvious that there's crazy things that have happened in the woods, to the degree that I think that our stories about the geology of Southern Oregon are not necessarily correct. Like there are...
Or complete.
Yeah, exactly. And so I'm always struck by just how difficult it is to piece together a story, number one, and then number two, to get people to accept it. Because in the Pacific Northwest, we have the story of J. Harold Bretz, right? Who was I think he was a geology professor.
J. Harlan Bretz. Oh, yes. Yes, the channeled scablands. Oh, he's one of my heroes for sure. He was an amazing man.
Maybe you can tell us the story of Harlan Bretz, because it's fascinating.
Yeah, I think he was a professor in Chicago, and he went out there and he saw what they called the channeled scablands, which turned out to have been formed by multiple phases of, you get ice dams on these glacial lakes, and then the dam breaks, and then what happens is you get all this water coming out all at once. and the the water flow rate was so high and it was so thick that you actually form these features called anti-dunes, which you only get with very rapid, thick flows of water. And he saw these things and he recognized them as being from giant floods. But a lot of scientists didn't believe him. But fortunately, he had a faculty position, he had tenure. And so he just kept working on this. And I think it wasn't until he was in his 80s that he finally got an award from the Geological Society of America for his work, and that his work was widely recognized as being correct.
Yeah, and what was most interesting is that at the time, there wasn't satellite altimetry, there wasn't any aerial photography. The guy literally pieced together the story of what happened by walking the landscape.
Yeah, that's amazing. I know, that's really amazing. Yeah, like the whole thing about Madagascar, actually, in terms of stories, you're talking about that. I mean, clearly, what I'm looking for, is collaborators. And the whole reason why I was able to get to Madagascar was, first of all, I'd seen this work by Kelleton and Sheffers, and then Google Earth came out, and I could see that the most prominent feature in the area around the Indian Ocean were these giant chevrons in Madagascar. And I had, in Australia, I'd been working with Ted Bryan, who was a tsunami expert, and I'm trained more as a marine geologist, geophysicist, so I didn't know that much about tsunami deposits. And then Ted invited me and this Russian guy who was a tsunami modeler, but also was interested in tsunami deposits, not only from earthquakes, but from extraterrestrial objects. His name's Slava Gusyakov. So he invited Slava and I. He got some funding from his university, because what happened, what started it all was I read Ted's book called Tsunami, the Underrated Hazard. And I just shot him an email and said, I really like your book. And so Ted then invited Slava and I to come to Australia to look at his field sites. So we went there and we just kind of talked about things. And then I think I went back one more time, and that was when Google Earth came out, and I saw these features on Google Earth. So I sent pictures to Slava and Ted, and I said, look at this. It looks like there's really something going on here. So at the time, the Russian economy was doing pretty well. And so Slava convinced a Russian remote sensing company to fund us, because this wasn't something you could get funded through the National Science Foundation. So he told them, it's not going to and he figured out how to do it. He said, okay, we can do it for less than $20,000, which scientifically is cheap. Mm-hmm. And so with that money, we got plane tickets. Bruce Massey unfortunately got sick. We bought him a plane ticket, but we got a plane ticket for Bruce and Ted and me and Slava to go to Madagascar. And also, the other thing that helped was that there's an institution, a seismic group called the IRIS, that funds like seismic sites all over the world. And they were funding the only PhD level seismologist in Madagascar to run some seismic stations. And so Slava knew this guy. His name is Gerard Ramanabola. Malagasy names are really long. So Slava contacts Gerard and says, well, we'd like to go in the field, but in Madagascar, people speak generally Malagasy and French. They don't speak English. So Slava worked out this deal that we would borrow Gerard's 2 graduate students. So these are the only 3 seismologists in the entire country to go into the field for 2 weeks, and they would go with us and help out. But mostly they would be our translators, because they spoke English, French, and Malagasy. Mm-hmm. And we needed all of those languages to work in the field. And the deal was that we would pay each of the grad students $12 a day, plus their field expenses. We couldn't have done it without IRIS, which, by the way, was originally started by this guy who used to be at Lamont named David Simpson. So, and then also the other thing was that we didn't realize that in Madagascar, it's impossible to rent a car. So Gerard, just remotely, like now you think, oh, you go to a car rental agency, no. So Gerard arranged for us to get 2 4-wheel drive vehicles. We paid for it all, but that were driven from the capital of Madagascar, which is in the sort of middle of the island, down to the south where the chevrons were, because you couldn't rent a vehicle in the southern part of Madagascar. And so these guys drove the cars down to the trucks to meet us at the airport. And it took them like a day and a half to drive down because the roads are terrible in Madagascar. So basically, this was an international collaboration, and we needed it. Slava got most of the money. Ted and I contributed some money, and Ted was a tsunami expert who really knew what these things looked like in the field. I was the person who kind of had the big picture idea to a certain extent, and Slava also knew something about tsunamis and was very technically competent. So he'd also done a lot of field work, so he kind of knew, how to do the logistics. So that's how we ended up getting samples in Madagascar.
And what was the publication that came out of all of that?
That was the 2017 paper that I sent you that came out in that book. We also wrote a short thing for the Tsunami Bulletin Board, but without actually having some age dates, and also the samples that I collected, looked at their grain size distribution, and the grain size distribution was completely wrong for stuff that was windblown. So I did a bunch of lab work on the samples. And I also looked at the marine microfossils, and they also had the wrong composition for being things that were just right on the beach. They looked like things that had been eroded off the shelf, which is exactly what you'd expect if they were tsunami deposits.
And that one was the younger Dryas deposit, or that one was 536?
That's the ages. If you average the ages, it's younger Dryas. And I mean, these things. I mean, the thing that was so impressive about this thing was on Google Earth was that you could actually see that these things went, tens of kilometers along strike, and that one of the chevrons, the one that's called Fenambus, it went inland, and there was a big fault scarp, and you could see that the sand had gone up this fault scarp. And it's like the top of the fault scarp is like 175 meters above sea level. So you could see that the sand was, not as thick up there because it didn't, but you could see that it looked like this thing had gone, really far above sea level.
How many people are studying this along with you? Is this a big field? Are there a lot of people that are pursuing this sort of enormous unknown tsunami story, or are you kind of
there are people who are looking at tsunamis deposits for sure, but I think but there are people who are looking at things like tsunamis from big landslides, and of course there's tons of people who look at tsunamis from earthquakes.
What's really interesting to me about this whole story is that we tend to think of impacts as being a 1 in a million situation, something that happens in the distant past and would never really be a problem today, or if it was, we would have adequate warning and so forth. But it seems like this picture is one where these impacts are actually quite frequent. What's our future look like? Especially with regard to the cometary type bolide, the things that erupt in the atmosphere, because from what I understand, NASA is doing a pretty good job of tracking near Earth orbiting objects, but it seems like comets and so forth would be transiting, and a lot of these comets don't appear very often in the human record, right? They're long period. They might come every tens of thousands of years, if that. How set are we for the future?
Well, it's a problem because we still can't see the really small objects. But the new space telescope that went up can see in the infrared, and that's really good for imaging cometary type objects. Because they tend, until they get close to the sun, a comet will look dark. So what people, asteroids...
Because their jets aren't shooting yet, right?
Yeah, that's exactly right. So until they get close enough to the sun to start losing water and ice vapor, they look dark, and they tend to have a dark coating on the outside. And so they're hard to see with a conventional telescope. But because they're dark, they absorb heat. And so that means that they're almost what they would call perfect black body. And so they absorb heat. And so that means that they emit in the infrared. And so a telescope that can see in the infrared can see comets more readily.
And I guess we have some pretty cool programs to deflect comets and asteroids at this point. There's been a few remarkable demonstrations. I'm thinking of the DART mission in particular. Because you only really need to nudge these things a tiny bit to get them off course, from what I understand.
That's right. And so that there are plans to, try and nudge one of these things out of the way just by basically heating up one side or something like that, So yeah, they've got some pretty good plans. The real trick is to detect them to begin with and to calculate their orbit.
Yeah, it seems like it might be a problem that we have to solve sooner than later too. I feel like we, as a culture, have this idea that these impacts are so infrequent, but the data is really painting a picture of something that we can expect to happen in the next, honestly, few hundred to 1,000 years. It's not something that we can push off forever and let our descendants deal with it.
No, I mean, there was the recent impact in Chelyabinsk in Russia. And again, it's lucky that so far these things have happened in areas where there weren't so many people. In Chelyabinsk, nobody was killed, but there were some people who they were near windows, and they got cut by the glass that was blown out of the windows. So yeah, I mean, we do need to prepare for these things. I mean, the Tunguska size events, I mean, they used to say it was like 100-meter diameter object, and now they're saying it's more like 60. And the thing about Tunguska is, if Tunguska event happened over New York City, I live 30 miles from the city, and I'm at the edge of the area where the trees would be knocked down. So you can imagine an area where probably, the greater New York area is like 20 million people. And so, basically millions of people would be affected by a Tunguska sized airburst if it happened to happen over a major city.
Mm-hmm.
And 30 meters is modest compared to the tsunamis that you're talking about, the impact that results in the tsunamis.
Yeah. And I mean, I think one of the reasons why people discount, these events happening is they think, there still is Bruce Massey, who's one of my collaborators, did write a paper saying that there's basically a deficit of known impact in the last million years. So just based on the statistics. But then again, the biggest problem is that these things are random, and you can't really predict when they're going to happen. So you still could have a big one. But also, the Tunguska style events, they happen every couple hundred years. So if you happen to have a Tunguska event over a major metropolitan area, it would be a problem.
I would be remiss if at this point I didn't mention the work of Lance Weaver, who is a geologist in Utah. And he has been looking at the evidence of the last glaciation and has noticed that the position of the North Pole appears to have been over Greenland rather than over the North Pole.
The glacial North Pole, like the center of the glacier.
Yeah. And so basically what he's saying is he's like, look, if you look at the edge of glaciation across North America, you can look at these lakes. I think it's the Great Slave Lake. I don't remember any of the other ones that are on the arc of the glacier.
What a name, by the way.
I know. But his point is he's like, look, I think that there's decent evidence for being able to say that the North Pole might have shifted during the last glaciation. And there's also, do you know the work of Charles Hapgood?
Yeah, I don't really believe his stuff, but it is true that the magnetic north moves around.
And so why is it not possible for the crust of the Earth to shift?
Well, I think it is possible to happen over long enough periods of time. But, I mean, he's wanting it to happen over ridiculously short periods of time.
Well, I think that one of the most interesting things from Hapgood's book is that they discovered fully preserved, perfectly preserved mammoths that were in the permafrost, whose meat was still good enough for the sled dogs to eat. And when they uncovered their stomachs, they were filled with prairie tundra wildflowers like buttercups, summer mosses. And so he's like, look, if this thing died and then in the summer with its belly full of summer meat, or summer food, then the meat wouldn't have been good and the dogs wouldn't have been eating it. But when it was uncovered and melted from the permafrost, the meat was good and it spoiled within a few days. And so there's these weird anomalous things. And they found a couple of mammoths that were, I think that their hips were broken and it looked like they had fallen from great height and then immediately died. And again, with this sort of the summer diet in their stomachs and were preserved perfectly. And so there's these oddities. And also, it seems like when the glaciation happened and formed these North American lakes, that Siberia, the lower parts of Siberia weren't glaciated. So it seems like it wasn't that there was this downward extension of glaciers. He's proposing that there was a different origination point for the polar glaciers that seems like it was farther south. And, you know, from a layperson's geologic look at the evidence, it does seem plausible that there was a shift.
Yeah, I don't believe it. I just don't believe it. And I mean, Siberia is pretty dry, so I think it's plausible that there just weren't any glaciers in Siberia because it was too dry. I mean, you do get polar deserts, so.
Yeah, it's an interesting proposal. It was taken quite seriously at the time. I know that Einstein wrote the foreword to his book and toyed with the calculations a bit for a while, but ultimately came down on the side of it not being plausible in terms of the viscosity of the underlayer of the crust and the amount of mass necessary at the poles to twist the crust and so forth. But the record of the extreme changes in climate persists regardless of which side you come down on with the Hapgood business.
Yeah, well, there have been changes in climate, and I mean, what we're finding is that I mean, the ice core record shows us that the changes in climate happen much more rapidly than people expected.
Mm-hmm.
So, I mean, some of those mammoths actually, I have a friend, Jonathan Hagstrom, who's been working on them, and he thinks that there was an impact event up there, and that some of the mammoths who have broken bones and things, they actually look like trauma victims.
Mm.
So
that would make sense.
There's something else going on there.
You said something earlier about our perhaps insufficient understanding of climate models in terms of being able to understand how these large events can change the climate. Can you elaborate a little bit on your vision of that?
Well, I mean, okay, I'm not a climate modeler, but well, there are things like one of the things that people don't understand is that there's something called the mid-Pleistocene transition, and a lot of the claims changes in climate are driven by changes in the Earth's orbit, the so-called Milankovitch cycles. But what happens in the mid-Pleistocene transition is that the period of the cyclicity changes, and they don't understand why. So yeah, there's still a lot of things we don't really understand about climate. So and also there's some suggestion that sometimes it gets colder in the northern hemisphere and warmer in the southern hemisphere, and that they're like out of phase, and they don't understand that either.
That's really weird. Yeah, so there's a lot of chaos in the mix. There's events that must punctuate the greater cycles.
Yeah, I mean, there's also something I've seen where they talk about a theory of chaotic attractors. That's one of the reasons why they're so worried about global warming, because, I mean, basically the climate system, the whole atmosphere, it's a very chaotic system. And so what you can have with a chaotic system is that you have multiple stable states. And once you get the system into a given stable state, in this case, it would be, if we have global warming, you get it into a stable, warmer state, you might have to get it a lot colder in order to get it back to the prior stable state.
Mm-hmm. Did you have a hard time as a female scientist in geosciences when you were coming up?
I was sort of at the beginning of where there were a lot more women. I mean, when I was a grad student, there were 4 women out of 20 grad students. And that was the most they'd ever had. And then by the time I left, it was like half and half. So mostly it's not a problem. I have sometimes found when I'm at meetings and we're standing and talking, I'm kind of short, and the guys will talk over my head. But so sometimes there's a problem that people don't listen to you as much. But I think it's changed a lot for the better.
That's reassuring to hear, because I feel like there's a tendency to see it as still being kind of catastrophic, but I do see a lot more female figures in the field. Do you think that there's a difference in the way that you encounter the evidence than your male colleagues?
Not really. I mean, the people that I'm working with are mostly guys. I mean, I think it just depends on what I think really matters the most is whether or not somebody's like a big picture thinker or more detail oriented. And that has nothing to do with gender. And I tend to be more of a big picture thinker, and I have to really struggle to like check all the details. And then there are other people who, they're very good at all the minutiae and they struggle with the big picture.
That's what teams are for, I guess.
Yeah,
really.
Yeah. And I always like to work with somebody who's very detail oriented. At least we'll have one member of the team who's that way, because I know that's not my strength.
Yeah, I think the best scientific endeavors are partnerships on that order, where you have somebody who, I'm publishing a paper right now. It's the same thing. I look at the author list, and it's an amazing team of engineers, mathematicians, theorists, and experimentalists who are all doing what they're cut out for, essentially. And I think that that's always been the case in science, and I think we've talked about this a bunch on the show. I don't want to beat a dead horse, but there's this myth that persists of the lone genius in a lot of different praxis in human endeavors, but particularly in science, we love to have these heroes. But if you really peel back between the lines of the history, you find really strong networks of correspondence, of collaboration, of people solving these problems by bringing their particular diverse skills and talents and curiosities to the table. And I feel like that doesn't get enough attention for new students especially, and people who are looking to move into the world. If you want to be an entrepreneur, if you want to be, I don't know, a Navy SEAL, if you want to be an artist, you have to be able to form really valued relationships with your peers and contribute and use their talents and build these networks. It's an interconnected universe, and we can't ignore that.
No, it's you absolutely need collaborators, and I mean it's just critical. And if you look at, like, for example, Science and Nature papers, which tend to be the top papers in the field, a lot of them, what you see is like the lists of authors. There'll be like 10 authors, 15 authors, and that speaks to the need for collaboration. That it's very difficult. You can't be an expert in everything, so you need to bring in people who have their own field of expertise. And also, it's extremely difficult to check your own work. So you want to have somebody else on the team who can just read over the paper and say, "Hey, are you sure you meant that there?"
And that's exactly what Nature told us the first time we sent it and got rejected was, hey, you need to bring a completely different angle to this story, a completely different method. And so we had to go and find people at other universities who were working on the same problems and get them to check out our problem from their angle and really build a whole, like, the paper doubled in scope by the time we were able to publish it. And so this is how it works in every field of humanity. And it's so, I don't know why this gets lost, It's
Yeah, it does get lost.
People need that vision of the singular genius for some reason, but it never plays out that way.
No, well, I mean, the one thing I heard was that at one time at Berkeley, which I'm sure this has changed, but it used to be that the department was mostly paleontologists, and in order to get tenure, you had to publish something like 5 or 6 sole author papers, and that was fine, I think, for paleontology, but particularly when you're doing marine science, you're going out on a ship. You can't get a shipboard program funded as the only person. You can't be the only person on the ship because somebody has to stand watch for 24 hours a day. So you need a team. So everything in marine science, pretty much, if they're going out and collecting primary data, it's always multiple authors, multiple collaborators, just so the ship can get used for 24 hours a day.
100%. And honestly, that's my favorite part of this podcast too, is that we've started to build a real team of people. I wouldn't have found out about your work without one of our patrons. I believe it was Tim who sent me the New York Times piece. And this is such a rich environment to probe nature and understand how things are working, because I can't possibly be out there digging into the far reaches of the internet and the history and the past and what's happening. And I just can't imagine a more productive way than aligning yourself with people with mutual interests that are complementary, not necessarily doing the exact same thing as you. Right? I spent a lot of time thinking about molecular atomic things, but I'm really interested in all these other things, and they play into the bigger picture of nature and of the world.
Yeah, I wonder if the environment for finding collaborators has shifted with the advent of the internet and email and everything else, because it seems like it would be much easier now than it ever was before to find somebody who's working halfway across the world on the same question that you're interested in.
Oh, absolutely. The internet has changed things, because I would never have met Ted Bryan if I hadn't been able to email him and say, I really like your book. And then the same, how did I meet? Oh, I did meet Slava Gusyakov at a scientific meeting. He went to a meeting in Japan. So we were both at the International Geological Congress in Japan. That's how I met him. But yeah, scientific meetings, I just went to a meeting in New Zealand, and I have hopefully picked up a few collaborators from that meeting. But yeah, without the internet, it's so much harder, because the other thing, of course, is like here I've got collaborators in Australia and Russia and all that, and the time zones are really crazy. So email is perfect because you can send somebody an email, and then they'll answer it like 12 hours later whenever they happen to get up.
What are the collaborations that you're hoping to develop with the people that you met at the New Zealand conference?
Well, they're interested in volcanic eruptions. So I've got this stuff that I found in the ice core, and I found submarine microfossils and things that looked like cosmic dust, but most of what I found was volcanic ash. And so I need some people who were more expert in volcanic eruptions to work with me to help publish that data. I figured out two other things that I'm kind of trying to get published first, and then I'll publish the last of the ice core data.
When it comes to something like the younger Dryas impact, do you expect there to be a period of increased volcanic activity that corresponds to it?
I was thinking about that today, and I want to check it out, because if there was a really huge impact, you would expect that it might affect volcanism.
Just on the basis of deforming the Earth and then causing reverberations through the mantle that then come up in other places?
Well, yeah, I mean, if it actually affected the mantle, then it would be more complicated, because there's some people who think that mantle plumes, which are these really, where you have really big volcanism, that they're affected by impacts. But the problem is that then there's like a time lag of perhaps 10,000 years before you actually see the effects.
Okay, so this is something that I really want to ask about, which is that we were looking at the spreading rifts on the bottom of the ocean floors, and the current model is that you have these convection cells and there's updrafts at the ridge, and then you have the conveyor belts of the ocean floor spreading away in either direction and then getting subducted at the margins. But when you look at the mantle plume data, it doesn't seem like there's a really clear line of upwellings underneath the ridge. What do you make of that?
Well, there are some, but you're right. Not all of the mantle upwelling is underneath mid-ocean ridges. And I think part of that just has to do with the length scale of convection that basically convection cells like to be 1-to-1. And so if you're more than 2,000 kilometers away from mid-ocean ridge, then any mid-ocean ridge, then that there's probably the mantle would sometimes like to upwell, and there's no ridge for it to go to. So that's part of it.
Does it complicate the picture somewhat, though? Because if you look at the age data that's based on the magnetic change, it's a very neat picture, right? So you look at these age floors of the ocean floor, and there's these clear gradations of, on either side, this took this long to form, then this long to form, then this long to form, and it seems like it's this very clear line along the entire length of the ridge. But if the mantle plumes are not centered on the ridge like that perpetually, then how is it that you get such a uniform spreading?
Well, it's actually, the spreading is somewhat asymmetric. And I think mantle plumes do affect that.
Mm-hmm.
But one of the things that happens is that ridges tend to jump to plumes. So the ridge crest can actually jump to a plume, because then it's easier for the upwelling to occur.
And there's another thing in the Pacific Ocean. Do you know these? I think they're called guyots. Guyots. There we go. I've never said that out loud. So the guyots, they're these flat-topped mesas that are underneath the waves. And there's a lot of them that are in the Pacific, but they're not in the Atlantic. And so is it do you think that it's possible that they're somehow related to this impact event?
Not that I know of, although that's an interesting question. I mean, there's two kind of, okay, the classic theory of geos is that they were seamounts that were close to the surface of the ocean, and then there was a coral reef built on them, and then they sank. And so the coral reef made the top flat. But it turns out that there's some new knowledge that I learned about with Hunga Tonga, that they've now found out that if you get a volcanic eruption that's pretty close to the surface, but it's mostly underwater, you can actually like scour the top of the seamount and make it flat.
And that was the thing that when I was looking into this, I was astounded by how many of them there were in the South Pacific and how flat they all were, and the fact that the rising sea level explanation would have made sense if they were also in the Atlantic. But the asymmetric distribution to me seemed like it was indicative of something specific that happened in the Pacific Ocean rather than the Atlantic.
Yeah, I think there are more seamounts in the Pacific. That's part of the story. But yeah, I mean, at one point, these things were close to the surface, and they were they were probably volcanic islands. At least that's what. And then they subsided. And what they've learned is that a volcanic island, after it erupts, it can almost immediately subside like 1,000 meters. So yeah, I think
is that
right.
because of that's a crazy amount of subsidence. Is that because the magma chamber is depleted and then the ground sinks down into the now empty chamber?
That's right. You lose all the magma and then the whole thing subsides. But there's also an area of the Pacific called the superswell where they think the seafloor is anomalously shallow for its age. So you're right, mantle plumes do affect the elevation of the seafloor. So perhaps one of the explanations for all these seamounts in the Pacific. I mean, what you really have to have had is you had to have had an area that was geologically young, like probably an area near a ridge crest, where you had a bunch of seamounts, because most ridge crests, except for Iceland, are not subaerial. So you had to have had a ridge crest that was pretty close to sea level. Like I'm just guessing that it was within. Well, I mean, to get coral reefs, it has to be within a couple hundred meters of sea level.
Mm-hmm.
So you had to have a ridge crest that had seamounts on it, and it was also, of course, tropical, that were building coral reefs, and then they subsided, and the coral reefs, of course, would make it flat, and then when it subsides, you get a geo.
But how does a coral reef make a pointy mountain flat?
Because what happens is it has to be around for a while. That's a good question, because normally at the beginning you just have this peak, right? But what happens is that the coral reef keeps growing, and as the mountain subsides, so it also has to be subsiding at a rate that's just right. So the mountain's growing upward, or the coral's growing upward at a rate that's fast enough to keep up with the rate at which the mountain is subsiding. And then eventually what happens is that the coral grows so high that it completely covers the peak of the mountain, and you have this coral atoll, and that's a pretty flat thing.
But I can imagine the rate of growth and subsistence being commensurate in a couple of places. But there's thousands of these flat top mountains, and that to me seems like a discrete event that shaved them as a whole, because the perfect match of growth and subsidence that results in this perfect flat top over and over and over again is, I mean, I don't know what the statistics on that would be, but it seems like an easier, more parsimonious explanation is that there's a discrete event that causes the change. And I haven't seen this in the literature, right? Because I know that the conventional literature explanation is the coral reefs and the sinking and the erosion by the ocean movement. But if there's an impact in the South Pacific and there's an enormous wave that propagates outward that by the time that it gets to Madagascar is running up hundreds of meters, then it seems possible that these little mountains would have been flattened by that. But I haven't seen anybody who's looking at that in the literature.
Yeah, I don't know. I mean, they've drilled some of them, and they did find that it was a volcanic mountain and that the coral had grown up over time. Like the atomic bomb tests on Weetalk and Bikini. So, they drilled some of them, and it seems like the history of the coral growth does kind of support that model.
Mm.
But that doesn't mean that every one of them formed that way. It just means that the ones that they happened to drill did seem to support the model.
And that's what's so interesting about these events that are global in scale, right? Because you drill a couple of places and you build up a model for what happened in these couple of places, but that model isn't necessarily, until you've drilled a huge number of them and made the same discoveries at each and every single one, then it's hard to be able to say that the course of events that you discover in one place is going to be the course of events that holds for all of the places when you have such a large number of them.
Yeah, no, it's a very interesting question, and I gave you what I know, but I don't know if I think there's probably is something else going on, because the ridge crest would have had to be pretty close to sea level, and the subsidence rate would have had to be just right if it's really all coral reefs.
Yeah. Do you think that there is still a lot of paradigms in geology that will shift over the course of the next 10, 15 years? Are there things that you look at where you're like, this is about to break in a different direction than we currently think that it is?
Oh, probably, but I don't know if I can predict it. Usually with data, I have to kind of look at the data and kind of say, oh, well, it looks like it just doesn't, this model doesn't fit the data.
Mm-hmm.
It's pretty hard to just kind of predict what's going to happen.
Mm-hmm.
One thing we kind of skipped over with the tectonic convection cells that's pretty interesting. We recently had James Garvin from NASA Goddard on to talk about Venus and Hunga Tonga also. We really got into that. But Venus has all sorts of convection, but it doesn't have this plate tectonic motion. And it's a real puzzle when you add that into the geology on Earth, why these two systems, these two planets, have this convection, but only one of them seems to have these motions to it. I look forward to some paradigm update about that in the future, and I'm not sure what it will be.
Yeah, well, I think the main thing you need for plate tectonics to work is you need two things, actually. You need the basalt to eclogite transition, because they talk about slab pole. So you need that. But another thing that you need that isn't discussed very much is, I think the presence of water is pretty critical, because what you need to have at the bottom of the plate is you need to have a zone with very low viscosity, and the presence of water helps you there. So you need something that's sort of like silly putty. When you start to move it, it then becomes almost like a fluid rather than a solid. So you need, and I don't know. Venus has tons of basalt, so you could presumably make eclogite, but I don't know if it has enough water inside the planet to make. We call this region of low viscosity the asthenosphere. I don't know, and right at the base of the plate, it's basal, what they call basal shear traction. So I don't know if Venus has the right conditions at the base of its plates to enable movement.
That's a really good point. I think you did mention that there was a significant amount of water vapor from the recent eruption that they were watching, but he not personally, but they're going back, I think in 2030 to check this out, and they're actually going to land and start to get some samples from the floor and make sense of these questions a little bit. So that'll be really interesting if, really just what the difference is and what causes these two behaviors will be really, I think that's going to be an interesting paradigm shift as we understand it better.
I think it may be that the other thing is that if you have to have, it may be that you need thermal gradients that are low enough so that you actually get an eclogite. I think otherwise you get something, an amphibolite. So you need the right, I don't know. I feel like I'm getting out of my area of expertise here. But I think there are definitely conditions that are required for plate tectonics. And it's not so clear why they don't exist on Venus.
There was in the early part of the century, there was this big debate between the tectonicists and the expansionists, right? So Samuel Warren Carey was the expansionist voice of the fact that the Earth was once smaller, and the explanation for the age of the ocean floors was expansion. The plate tectonics guy was I can't remember his name.
Wegener.
There we go. Wegener. Okay, so we have Wegener and Hapgood. They're going to these meetings.
Sorry.
They are. Yeah, you gotta give the German.
I messed that up when I was lecturing one time, and my one of my students, whose last name was also Wegener, stood up and corrected me in the middle of the lecture. Felt like such a moron. Wegener.
So, okay, so we've got Wegener and Hapgood. They're representatives of these two dueling schools of geosciences. One wins, the other is relegated to the bin of obscurity, where there's definitely still people on the internet that are big proponents, but it's not the consensus. When you go to these big geoscience meetings, is there a current of this kind of disagreement about anything, or has the consensus been solidified? Not necessarily about expansion versus tectonics, but are there topics that people argue about like this? Or
oh yeah, absolutely.
What are those topics?
Well, I mean, the younger Dryas, and there being an impact in the younger Dryas. I mean, I've been at sessions on that, and there are people who get up and just say, I think you're wrong, and here's what our data says. Or, no, people, I think actually they've been trying to make the level of discourse more civil at scientific meetings, and I think they've managed to do that. But no, there are people who will just get up and say that they don't believe you.
Why do you think scientific discourse tends to erupt so emotionally? What is it about explaining nature that brings people to the edge of blows?
Well, I think one of the things that happens, and I think I'm able to say, okay, I did this and I was wrong about it, right? But I think there's a lot of people who can't do that, who just, they write something in a paper and it's like they feel obliged to defend that, even when the data shows that it's not right anymore.
So you think it's like a wider human behavioral issue?
Oh yeah,
like it just plays out. I guess so. Yeah, just in daily life, like the hardest thing in the world, I think for almost everybody, until you really master your ego, is admitting when the evidence piles up that you did something wrong, being able to be like, yeah, I could have done that better. That's messed up. I'm sorry.
Yeah, people get very wedded to their theories, and I mean, one of the things that I've heard is that a lot of, like, the people who are against plate tectonics, I mean, basically what happened is not that there are a few of them who changed their mind, but most of them died. People don't change their mind that often. They just kind of get into a certain mindset, and and you'd think that scientists would be better about this, but actually a lot of them aren't.
I mean, is there a real threat to someone's career to change their mind? Let's say prizes are given and you've achieved great status with a theory that you change your mind about privately. Is there a way for scientists to walk back on their ideas in a way that doesn't threaten their livelihood? Or what I
would say, that what somebody once said to me was, if I'm wrong, I want to be the one who writes the paper that says I'm wrong. So if you can be on top of it and write a paper that says, well, here's what I said in the past, but I think that the new data supports this idea more, then you're well ahead.
That's a really good point for life in general. I feel like if you can, that's the ultimate mastery, is being able to recognize when you've done something wrong before somebody else gets their feelings hurt or points it out, right?
Yeah, that's probably true. I mean, I wonder if it is just pride, or if it's also something that is deeper than pride, where people really believe that there is a deeper value to the explanation that they have offered beyond it just being their explanation. Does that make any sense?
Even if they're wrong, though, that's what I don't understand. Like, if you realize, I think people might maybe privately realize, this isn't maybe the best idea, but they're unwilling to move past that still. That's probably more common.
Yeah, but people also, I mean, I teach undergraduates, and one of the things we do is we teach them how to read a scientific paper. And what we find is that, I mean, it's like 25 or 30% of papers out there that get published. And you read the paper, and what we always tell them is to look at the figures first.
Yep.
See what the data says. And then you sit down and you read the paper. And a really high percentage of the time, far more than you would like to believe, what they're saying about the data is not the same as what the figures show. And what has happened is they usually, to do like big science, you have to get a proposal funded. So you wrote a proposal and you said, okay, I think that we're going to find this. And then people kind of get that in their mind that, oh, that's what we're going to find. And that even if their data shows that they didn't find that, they still write the paper, the text of the paper, as if that's what they had found. Because they just got it in their heads that that's the right explanation.
I think that is the central mind virus here. I cannot thank my advisor enough for teaching me the lesson that no matter what this he would always say this. We'd be planning an experiment, and he'd always say, it doesn't matter what happens in this experiment, it's going to be interesting. And I love that.
Yeah, that's what I'm telling my students, too. I don't want them to be disappointed if we don't find what we were expecting to find, or what our central hypothesis was. So I tell them, look, it's going to be interesting no matter what. And actually, sometimes I like it better if we find something different than what we expected.
What are some examples of times that you have gone out into the field expecting one thing but found another?
Oh. It's more like in the lab. It's like this ice core work that we did, where we were looking for cosmic dust because Mike Bailey had written these papers saying that that in this time period, like they were saying that the stars were dancing, and he thought that was because there was more cosmic dust coming in. So when we were doing this ice core work, at first we were just looking for bright stuff because cosmic dust is metals, and metals, they reflect more when you're using a scanning electron microscope. So we were just looking for bright pieces. And then we started finding things. It turned out that volcanic glass was bright. And then we saw these marine microfossils in there. And we're like, huh? We didn't expect that at all. And then, I found an expert because I couldn't identify them. And it turned out that they were tropical to subtropical. And that was a huge surprise. So yeah, that happens a lot. And we were pretty sure because of how we'd done the work that it wasn't contamination, that those were really there and they were really part of the ice core. But yeah, but I think some people, sometimes when they find things like that, they would say, oh, well, it must be contamination, and so I'm not going to publish it because, I'm too afraid. And I heard this story about this guy who was at Caltech, and he had some early data. I don't remember the details, but it was like he was getting temperatures from something that were like 120 or 130. And normally when you measured these temperatures, you'd get like 20 or 30 degrees centigrade. So he never published the data. But it turned out that those high temperatures were right.
Well, say more about that. Where were these high temperatures?
Yeah, I don't remember the details. I just remember that I think he was maybe measuring carbonates, and he was getting high temperatures of formation. I really don't remember the details, but I remember. But this was guy, like a distinguished professor at Caltech, and he was measuring these things, and he was getting these numbers that were, like 120, 130 degrees centigrade instead of the normal 20 to 30. And he just didn't believe the numbers. So he never published it.
I really, really wonder how often this happens, that people come across anomalous data, because this happened to me during my PhD, where I studied microbial biofilms, and we had a very narrow range of questions that we were asking. And as I was doing experiments, I would always find weird stuff. And the weird stuff would always be something that we set aside, where it's like, well, that's not relevant. That's not what we were focused on. Maybe it's an artifact. And I was always obsessed, because I was like, I think that might be where the mystery is. Like, I think that might be the thing that is the big question, and it might be the more exciting thing. But, like you said, there's proposals, there's arcs of the scientific stories that we tell, there's the limit of the focus of the lab, there's the question of what collaborators can you find to be able to ask and answer these questions. And so there's the field of science, to me, seems like it's just scattered with the corpses of these discoveries that people have made and just set aside because they don't have a story into which to fit them, and to find the story would require them to restructure their entire focus for the next 10, 15 years, because it's such a difficult story to tell.
Right. No, you like they say, chance favors the prepared mind. And that's really true. And one of the things that I know somebody who does carbon-14 dates for a living, and I think somebody told me this, that only half of all carbon-14 dates that are made are ever published. And some of this might just be that people don't have time to publish them. But I think also part of what's going on is that people get a carbon-14 date and it doesn't fit what they think it ought to be. And so they say, oh, this one was contaminated, this one was bad data, I'm not going to publish it.
Yeah, there was, we had a geologist on, and he was talking about something called the Hallstatt Plateau. Do you know this? In carbon-14 dates, it's called the Hallstatt Plateau, and there's this period of time where because when you look at the decay of radioactive isotopes, there should be this straight line curve from your oldest date to your most modern date, in which your relative isotopic abundance decays at a specific rate. But there's this period in the carbon-14 dates that's called the Hallstatt Plateau, where it just flattens for a period, I think, of like almost 1,000 years. And those are really difficult dates to be able to figure out, because if you're dating something that falls on the time period of the plateau...
It's right around the period of this 500 BC, eh?
I think it is right around the 500 BC period, where there's basically an oddity in the carbon-14 dates, where if it happens to fall in that plateau, you can't depend on your carbon-14 dates because it's a jagged plateau, and so it gives you all of these weird anomalous dates that don't fall in the decay curve. And people kind of know about it, but they also don't know how to deal with it. And so I think that what they do is they try to find other forms of evidence, like they'll look at I think tree ring data, they'll look at ice core stuff, they'll look at other isotopic measurements to handle it. But it is kind of a thorn in the side of radiocarbon dating, which is like what happened there to cause such an anomalous window of dates. And nobody knows.
No, you're right. There's a bunch of places in the carbon-14 timescale, and basically the production rate of carbon-14 in the Earth's atmosphere varies over time. It's not constant. And so, yeah, they have to, it is a problem that, and so when you actually get a carbon-14 date, the normal, if everything was like perfect and it was just produced at a constant rate in the Earth's atmosphere, then you would get what's, called a normal or Gaussian distribution of ages around some central thing. But in fact, what you can get because of these little plateaus and changes is you can get a probability distribution that has multiple peaks, and it's really wide. And I'm sure that where these Hallstatt plateaus are, it's ridiculously wide. So yes, it can be very difficult to interpret carbon-14 dates.
And this is kind of what I think about a lot in context of science, where we have models that allow us to speak with certainty about the past. And as long as the model is accurate, then it's reasonably certain that the numbers that you get off of the model are ones that you can kind of fit into a steady timeline of events. But we also know that there are issues with the methods, and there are problems with being able to really, really drill down deep and to pin enormous certainty on some of the dates. And so it feels like it's well acknowledged in the field that these are problems, but because nobody really knows how to address it, and because it would create such a destabilization for the entire field, right? So if dates are hooked onto incorrect readings, or the readings are somehow shifted by atmospheric production or by, there's a guy at Stanford who suggests that there might be like microbial alterations to specific environments that could change the rate at which the isotopes decay, that it's just really, really hard to fold those into the model because they create a discontinuity in your dates and an uncertainty that doesn't work with the way that we do science. Because at the end of the day, we want our science to be something that gives you a final answer that you can, put into a bound book and stick on the shelf and say, we're done with that, and then we can move on and use the methods across the board consistently. And I wonder if that is just a limitation of trying to look deep into the past, where we can cobble together things and we can say with reasonable certainty, but we'll never know for sure.
Yeah, I think that's a fair statement. I mean, I think one of the things that they always say is that what you should do is publish good data, and you should not spend you should separate your data from your conclusions from your data, because what happens is, as you just said, is paradigms, hypotheses shift, and people, and so like there's a whole lot of papers that were written about the Mediterranean before the whole idea of plate tectonics came, and they talked about eugeosynclines and myogeosynclines and Flish, and if they didn't talk about their data, then people just can't use those papers because the prior assumptions about what the stuff means, like you actually have to talk about the rock types, it's just gone. And so those papers get discarded. Whereas the papers where people, talked about, okay, here are the rock types and here's a map of where they are, and here is where we think the faults are, those papers survive.
Absolutely.
Yeah, and the bigger picture there too is that the story you can tell with certainty is necessarily different from the true story, because you're missing a lot of the pieces of the story inherently by looking into the deep past. And so it's hard to keep an open mind when you have such certainty about your data points, which might be very accurate, but they're not the complete picture at the same time.
That's right. There's also a tendency for geologists who are doing field mapping to, because the classic sort of geology thing was to give people like a quadrangle to map. And so before plate tectonics, people would just interpret everything that they mapped in terms of things that had happened in the local area. There would be like no effects from outside that little quadrangle. And of course there were effects that, things that happened that were, thousands of kilometers away that affected what happened in that little tiny quadrangle.
I really fantasize about having citizen science geology be more widespread, because do you know the app iNaturalist?
No, I don't know that.
So it's a machine learning plant and animal identification map. So you can snap a picture of a plant and you can upload it to the app, and then it will analyze the photograph and tell you what the plant is. And so if you make really, really good observations, they're classified as research grade. And so researchers that are trying to figure out the range of plants and animals can turn to this enormous data set, because it has a huge number of users that are really, really passionate and they can actually use the data that's collected by people as they go out and snap pictures on their hikes to then do research. And geology is one of those things that I feel like is apparent on the landscape, but there's not a huge contingent of people who are there's not a way for the average person to learn about it and then to be able to contribute to geosciences. But exactly like what you're saying is that our mode of mapping is, yes, we map these quadrangles and we look at what the rock types are, and areas that are of particular interest to researchers will get a lot of attention, but there's huge swaths of the landscape that don't get as much attention, and yet there's probably hidden geologic stories that are happening there. And it would be such an incredible thing to be able to go out into the world and to take a picture of a rock or a landscape, and then to be able to put that into the flow of research and to have a community that's global in focus be able to start telling the individual stories of these landscapes on the basis of the things that people find. And I wonder if that's even possible, right? Because you can take a picture of a plant and the leaf shape is what tells you what plant it is, but I don't know that you can take a picture of a rock and just off of a cell phone picture of a rock be able to identify what the rock is.
No, you can't. You can't really do that. I mean, there are things that you could take pictures of, like people are always looking for, where rocks are cross-cutting big dikes and things. Those I think would be useful because people use them for dating and things like that. So I think there are certain features, and I know that they've been doing in Scandinavia, they've been doing citizen science for looking at impact craters.
Mm.
So I think there are things that people can do. But
how difficult is it to take a core? Like, could I go out into the woods and take a rock core?
no, you need a drill.
How big are we talking of a drill?
Oh, the rock drills are like this big around.
Mm.
But then, I mean, that's for paleomagnetism. But I mean, to be honest, I've gone out and done that, but I did it with my husband, and he was the one who held the drill, and I was pumping the water. Because they're pretty hard to hold. You have to be pretty strong. So
These are not battery powered hand drills or something. You were just making a sign of
it was
something
like
that
a
was like
chainsaw
6
motor.
inches. Yeah.
Yeah. And so we were
Interesting.
drilling samples for paleomagnetism. And then you had to like orient the sample too, so you had to know what direction things were in. So it was a fairly complicated process.
Mm.
I'm sure there are things people could help on. It's just, figuring it out.
Definitely. Well, what's down the road for you? Where is your focus headed to now?
Well, I'm trying to get, we just got a trove from Bruce Massey, we just got a trove of these myths. So what I'm going to do is go down and he had approximate locations for where they were, recorded. So I want to just like start making maps of where people recorded things. And also, a lot of these structures, we like the one in the Arafura Sea, we need more core samples, or we need a geophysical cruise over the thing. So I want to, if we can get enough other data, then I could probably get a cruise in that area, and we could actually go over the feature and see. Because I mean, underwater craters, if you have the right kind of geophysical data, I mean, there's some off the U.S. East Coast, and they're accepted because somebody ran a seismic line over them, and you could see things like there should be, if they're big enough, there should be a magnetic anomaly in the center. You should be able to see fracturing of the basement rock. So if you have the right kind of seismic line, you can get something where people are, at least for an underwater crater, where people say, okay, yeah, that looks like it's an underwater crater.
Very cool. I mean, I would love to catch up down the road and to see what new things you discover. The map of observations is really interesting to me because I feel like the difficulty of looking into these phenomena is that papers generally don't have really complete maps, where there's few papers that take an event and then are able to map it across the entire world and then to present it as, a single figure in a paper, because it's a tremendous amount of effort. Like, that has to be what the paper is about. And those are kind of few and far between because it's such an immense undertaking, but they're so valuable for being able to tell what actually happened.
Yeah, I mean, one of the tools that I use is this program that's freeware that was developed at Lamont. It's called GeoMap app, and you can just download it, and it has a lot of data sets already on it. And then you can upload your own data sets. And so I use that to, play with data.
That's very cool.
Yeah, I mean, you said you didn't want to do screen share. I can show you something I did with GeoMap app, which shows those 2 crater candidates that were derived from satellite altimetry if you want.
Maybe you can send us a link and we can drop it in the description so people can play with the data set directly. Is that possible?
Yeah, I can just send you the latitudes and longitudes of these 2 crater candidates.
Yeah, that'd be fantastic.
Perfect.
So
that I
people
just
can explore.
read. I just have an Excel file, and maybe the map. That I'll send you the map that shows where they are.
That'd be great. Yeah.
Yeah, because I mean, one of the things we really need is just more core samples, and there are various databases, so to be able to access more samples.
We have we're friends with Avi Loeb, who's planning an expedition to Papua New Guinea, and they're planning on they're hiring a research ship, and they're going and they're looking for evidence of extraterrestrial impacts, because he thinks that he's identified this interstellar object that came down into the ocean around Papua New Guinea. But he's headed in that direction, and so maybe we can put you guys in touch and see if he's.
Oh, that would be great! Yeah, because if they're collecting geophysical data, and then they absolutely should have a magnetometer on board, and that would just having some real data over that structure would be amazing. And it's big.
We'll put
it's
you in
like 30
touch.
kilometers in diameter. It's huge. So
that'd be great. Yeah.
Yeah, and he's got the budget too, so he's done an exceptional job of rallying support for an idea that's outside of convention.
Yeah.
yeah,
Absolutely.
I mean, I'm interested in where he thinks there was an impact, because if this thing that David Sandwell found, he said it might be an impact crater, it might be a seamount. So, but yeah, if he's doing work it's southern Papua New Guinea on the Australia side, I mean, if he can get a ship in there, that would be fantastic.
Yeah, and I'm sure there's a lot of waste, right? I'm sure he's dredging up all sorts of rock that's not meaningful to him, but might be meaningful to somebody like you.
It would be nice to be able to get a few cores, so.
Yeah, we'll put you in touch. I'll send an email and connect you guys when we get off the phone.
Okay, and I'll send you the Excel sheet that has the locations of these 2 things, and a picture that I generated using GeoMap app that shows where they are in the world ocean.
Very cool.
Perfect. We'll link it for everybody to see.
Okay, great.
Yeah, it was a real pleasure talking to you. I really appreciate the breadth and scope of the work and how open you are to talking about it and how curious you are about the world. So thank you.
Oh, well, thank you. I enjoyed talking to you guys. I'm amazed at what we covered in this whole thing.